that look promising. I know it's going to be, it has to be basically a long-term research. If you can do it in less than 30 years, evidently it will be really great. But why the heck is nobody working on this? Okay. And the impact is that by having practical hash functions broken, how can we say that the research on digital signatures is doing fine? So you see all these beautiful papers that have all appeared, they all assume that you have basically a secure hash function. There have been people who have looked at truly proven secure digital signatures, but they are way too slow, and so nobody is even planning to use it, and we don't see how to make it fast in the next years. So I think that this is an important aspect that needs to be looked at. And I had a chat with the Quiz Quater, who basically agrees. He also thinks that the FSE community, basically the community that looks at conventional crypto, is on the wrong track. And also, if you look at hybrid encryption, since it relies, hybrid encryption says you're first going to start using with a public key, and then afterwards, once you have a session key, you will basically use a conventional crypto scheme. Also there, we have to rely on conventional crypto, and so a similar disaster should not be excluded. So I'm looking at, in blue, I know some of you may be colorblind, so we are at the level of foundations of modern cryptography. In there, we looked at lack of foundations for practical conventional cryptography, and now we're looking at incorrect security proofs. The most famous example is OAP, optimal asymmetric encryption padding, and there are many, 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 many more examples. Okay, and there have been people estimating, saying maybe a quarter of the proofs have no bugs. It doesn't mean the theorem is false, but the proof has a bug, and some people say 50% of the proofs are fine. So we don't know, and very few people actually are checking these proofs, except for very famous papers. Then what we have today is questionable proof techniques. The random oracle, for example, we don't know whether it's really, when we have a proof under random oracle, whether we have truly security. So it's, to say the least, the security is questionable. And I also think that we have another problem is the validity of our assumptions. So for 30 years, we have used RSA, discrete log, etc., etc. So many, many more problems that some of you may be familiar with or have heard about. So, but there are certain questions we need to ask about this validity of our old assumptions. How valid are these assumptions? It's a question, I think, which we don't know how to answer in the near future. But have we made any progress on finding some better upper bounds for the time it takes to break them? And any other comment, please. So the first is, it may take too long time. Basically, you're waiting for complexity theory people to make a major breakthrough, which may take a few hundred years or maybe 1,000 years. We don't know. So we just cannot wait for them. So, but then the question 2 becomes important. How have we made any progress? And the answer is really bad. It's almost none. The situation is truly bad. For example, the last time a major effort was made to develop a factoring algorithm was 20 years ago. There have been some improvements, I'm not saying that, but it's essentially today it's number field safe. And what does that mean? We're usually, so what we do when we talk about cryptography is that for the 20 years we have not evaluated the main principles of modern cryptography. And we claim to be high tech. I mean, talk to people who basically, that make laptops, and you say, oh, why don't you use stuff from 20 years ago? They are going to laugh at you. Okay? But that's what we as cryptographers do. We're using things that haven't been checked properly for 20 years. So this would be unacceptable in other areas, but we do it in our area. There are some positive notes. I'm not going to overstate. I'm trying to be giving a balanced talk. So there has been some work on proving equivalence between CDH and discrete log, for example, by Maurer. We also have this, basically the generic group model, which basically was generalized by Schupp in 1997. So I'm not saying that there has been no work, but it's definitely not enough compared to all the new schemes that are being made and proven secure. And it's kind of, what about the foundations, folks? What about the foundations? We don't look at those enough. And now another comment is that in the meanwhile, in particular Bonnet, every paper that's appeared by Bonnet almost has a new assumption. And why would they basically be secure? Okay, it's kind of, yeah, it looks, when you look at it, if you look at it quickly, you don't see how to break it. Okay, but it may actually make the situation worse. And then the question is, the worst scenario where you have an invalid assumption. So Abdallah and Poincheval in 2005 had basically an invalid assumption. And their assumption was a one-page assumption. And so far I remember, it appeared at Financial Crypto 2005, where they had a regular paper. And then the assumption was broken by Zidlow of, if I remember correctly, RSA Corporation. And he got the short paper accepted. So everybody asked him, said, are you not upset? These guys, they get a full paper. And you only get a short paper. He said, no, because I could indeed explain in these few minutes that the assumption was false. It was kind of, you divide this by this, and boom, the whole thing goes. Kind of looking at it, forget about all these things, just look at this, and now numerator and denominator, they cancel, and finished. Okay? It was a really simple attack. So the question is, from all the other assumptions that have been made, are people actually trying to break them? I don't know. Now, I'm not going to exaggerate, and I think we should definitely not rush the area of proven security, as for example, done by Koblitz and Menezes. I actually think it's one of the strongest things that have happened in cryptography, but we should be at least aware of the situation. Okay? And so if you look at what has happened in the computer security community, they also have done lots of research, for example, on key distribution. And there they are still in the cycle of you make a scheme, you break a scheme, and then you basically are going to hack it, and you hope it cannot be broken. So while I think in the crypto community, there is something that we can be proud of, that we can design key distribution schemes that actually have proofs of security. So I don't think we should rush the area of proven security, and that's definitely not the goal of this talk. So the second issue, the other two issues were basically, the other issue at this level was foundation of modern cryptography. The next one at top level in future research is classification of practicality. Today we don't have that. So evidently you could say you have the class of the research that has been successful, but then there are also those that are basically considered practical, but in reality when you talk to practical people, they got very close, but not close enough to actually make the thing practical. And as some of you know, I worked quite a lot on threshold cryptography. And so in threshold cryptography, for those of you who are not familiar with that, is you should just say, oh, this laptop, I don't trust this laptop. Maybe there's a bug in the Microsoft operating system. Maybe the hardware has a bug. And so you're going to say, I'm going to also want to rely not just on this platform, but I want to have another platform and possibly another platform, the one, for example, having an Intel, the other one Pentium, the other one having an AMD, the one running Windows, the other one running Linux, etc. And now, if I'm going to have to sign very important documents, so suppose the CEO of a company has to sign very important documents or very large transactions, financial transactions, then you don't want to rely on the insecurity or the claimed security of a single platform. You will only be able to produce this digital signature when all this, or a threshold of these the computers have actually been involved. And even if you can hack the security of less than a threshold, then you will still not be able to break the security. So you would think that this thing would be used widely, isn't it? The answer is no, it's not. Okay. So Shoup wrote a paper in 2000 in which he described the earlier work as much more complicated. And the earlier work was basically co-authored by me, so that's why I don't like Shoup's statement. And also states that in the previous work, the size of the individual signature share blows up linearly in the number of players, and gives his paper the title Practical Threshold Signatures. Now King, who actually is an associate professor a little in Indiana, a little bit more south from here, in ASACrypt 2000, he points out that the computations in the earlier work are actually much faster than in the, and that's for the case of passive adversary, than actually in Shoup's work. Okay? So it's amazing, isn't it? So it's not an improvement from the computational viewpoint. And Kramer-Fair, they present the black box secret sharing scheme, which has an exponential improvement. So it brings down the size of the share to logarithmic what existed before. But unfortunately, if you look at it, the computational cost of running that scheme, it's enormous. So something might be from one aspect more efficient, but not from another one. Look at the modern the laptop today. How much disk space do you have on that? Massive, okay? So it's not because you have a scheme that the size of the shares gets shorter, that therefore it's a better scheme from a practical viewpoint. So lots of things have improved on threshold crypto, but then it stopped and we are too far from being really practical. And so the consequences are that the Shub scheme is being used, although there are other schemes that in certain circumstances would be faster. But it's only used in the top security level of, for example, credit card companies. They don't use it. And so when you talk to people at, for example, Swift, they don't use it. And even if you have large transactions, they just use ordinary RSA or variants of that. And so you have to be very careful with statements of practical when theoreticians actually claim that something is practical. It's not necessarily practical. So there we have something which got close to practical, but never got there. So you have practical work, which is actually, I think, irrelevant. So you could say it took more than 20 years before you actually before hybrid encryption, proven secure hybrid encryption, got to where it is today. So I have to basically make a disclaimer, okay? So I'm not going to say that it will never be used, etc., etc. But so I'm not going to make a statement saying this is definitely impractical, etc., it will never be used. What I'm going to say here are more question marks. So the question is, will the following claim practical research areas ever be widely deployed? Something as if you look at SSH and SSL, which is widely deployed. And the example is blind signatures. Some concept of blind signatures is really nice. But where is it heavily used? Okay? I'm not saying that it's not used. There are few implementations. Undeniable signatures is newer, but any real-world applications? Not that I know. eCash and e-auctions, yeah, I mean, Google is using that to some extent. So there are nice ideas there, but also not widely implemented. The next two categories are practical problems that have basically not been studied, and those I will look at later. And there are also the impractical ones that basically are too important to give up on. And in that category, I would put secure multi-party computation. So in threshold crypto, what happened there is, so threshold crypto is actually newer than secure multi-party computation. Secure multi-party computation is an older concept. So it's similar to threshold crypto. You don't trust your platforms, but instead now of calculating a digital signature, you basically want to compute a particular function in multiple inputs. And you don't trust the participants who actually are involved. They may actually lie, and they may actually behave very badly, etc. It's quite clear that this is important. As long as companies are not being able to bring us computers that we can say we can trust these computers, then we need to rely on having different platforms in order to get something more secure. The problem is that today, this is very, 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 very far from practical. Now, if you talk to Ivan Damgaard, he will say, no, 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 I have an application. And what's my application? So his application from Ivan Damgaard is that he now is using that in the sugar beet auctions. So in the United States, sugar is made from cane. In continental Europe, due to the blockade of Napoleon, I mean, it was the British blockade against Napoleon, they basically couldn't get the sugar cane. And so therefore they looked at beets, and they actually now start to select the beets that have more and more sugar, and today that's still being used to make sugar. And they use very complex auctions in which the farmers try to get as much money, and the ones basically who are going to make the factories that are going to extract the sugar from it, they're basically trying to pay as little as possible. And so then they don't have to agree, they have to go in other